CNT140, Chapter 2, we're working through some of our cabling terminology. We're now on the section on fiber optic. So fiber optic is going to carry signal through pulses of light, if you will. A pulse of light representing 1, 0, no pulse of light representing a 0, so I'm able to transmit data with just pulses of light. This is typically going to be used as our backbone connection in our network, connecting our closets together, connecting our switches together. And we do this for bandwidth, but we also do it for distance. Because again, this closet could be across campus. And I might be using a kilometer-long fiber optic cable to connect this closet to this one. Okay, so we're typically going to use fiber optic for that connection. The type of fiber optic is characterized by the light carrying core and cladding. So we're going to do a little bit of refresher back from 120, maybe fill in some gaps, maybe fill in some things you didn't remember, to give us some basis for fiber optic. If I were to cut a piece of the typical fiber we would find in our, a building, a land building, if you will, building that you might be working in, here's what I find. I cut the jacket off. That's the protective layer on the outside. I then find strength fibers inside. Those are typically Kevlar, and they're there for strength, for tensile strength. If I got to pull in the cable, those strength fibers are there to try to take the bulk of that pull so it's not going to break the glass fiber that's inside. If I cut that away, now I do have a buffer coating. That almost seems like another insulation, if you will, but that's the buffer that's around the outside of the fiber. And then if I cut that away, now I'm actually down to the glass fiber itself, which if I put it under a microscope, which we will do later this semester, I can actually see that there is a cladding on the outside and a core on the inside. The two layers of glass, if you will, the core being the part carrying the light signal, the cladding being around the outside, almost like, a donut around the outside, and that's there to reflect the light or bounce the light back into the core. A fiber optic connection is typically two fibers, one for sending in one direction and one for sending in the other direction. So we typically see this type of connection where there's two fibers to make up a single connection between two switches. There is multi-mode fiber and single-mode fiber. Okay, there's multi-mode fiber, single-mode fiber. If I look at how the fiber handles the light, that's when you can start seeing the multi-mode, single mode. The single mode, the single mode has a very small core, and the light source is typically a laser light source. So I have a focus beam of light going into a teeny core, so I basically have one mode, one ray of light moving through the fiber, hence the term single mode, a single ray of light, a single mode of light moving through the fiber. If I look at multi-mode fiber, there's a larger core, either a 62.5 up here core or a 50 core here. Now the light source is typically LED based type of light source, and it's going to emit multiple rays of light, hence multiple modes. Multiple rays of light are going to get pass down the fiber to represent your data. This isn't multiple data streams, it's just multiple rays of light representing a 1. Multiple rays of light representing a 1. Okay, so don't let you think that that's multiple signals. It is not. It's one pulse of light going down is just made up of multiple modes, multiple rays of light. So there's your multi-mode large core LED light source. Multi-mode, this is your 50. This is your graded index fiber. I still have multiple rays of light, multiple modes, but they're being refracted, bent back into the fiber. And then we have our single mode down here, very small core, a laser light source, very focused beam. If I put the dimensions next to them, you start seeing here's your 62.5 core, 125 cladding on the outside. Your 50 core here and 125 cladding on the outside. And down here we're around 9 or 10 for your core with 125 for the cladding out here. And that is your multi-mode fiber and your single mode fiber there, just to give you a differentiation. And then there's the sizes. There's your step index 62.5, 125, graded index 50, 125, and single mode 9 to 125. You notice the outside, the cladding is standard among all of them. Here's kind of a diagram to show you the difference between if I had to look at the end of them under a microscope. 62.5, nice big core. 50, still a big core. Your single mode 9, that's a teeny tiny core. Teeny tiny core. Your multi-mode fiber, again, is typical LED light source. 850 nanometer light source, the wavelength of light source. This is typically used for short distances for LAN use. And we're talking hundreds of meters, not thousands of meters. Meanwhile, your single mode fiber, the core is tiny, and my wavelength of light is a lot longer. We're in the 1310 to 1550 nanometer wavelength, a lot longer wavelength of light source, so it's going to be able to go longer distances. So we're now into the MAN and WAN use, connecting buildings and potentially even connecting across towns, if you will. We're in the thousands to tens of thousands of meters. Again, multi-mode short links, 5125, 62.5, 125. And then here would be, this I think is the chart they have in the book showing you the different types of fiber and what they're used for. As we move on to terminations for UTP. The connector we use for UTP is typically going to be a modular 8-pin connector. The RJ45 is kind of a slang name. The actual connector for like a patch cable, this guy right here is a modular 8-pin connector. And this is used for stranded core for patch cables. Stranded cord called patch cables. Okay. The other type of termination, and this would be your patch cable termination here, this modular 8-pin connector. The other type of termination is your outlet jack. Okay, your outlet jack. And these, the wires are going to get punched in some format to terminate the outlet. And there is a color code order for these. I didn't mention a color code over here. There's a color code order here for the color code order for the patch cables. There's also a color code order for the outlet jacks. But this is your outlet jack termination here. We will do both of these. We'll do the outlet jack and then we'll also do the patch cable termination. But just recognize this is typically called the outlet or work area outlet or outlet jack. This over here, typically called modular 8-pin connector. That's what I try to call it. RJ45 is kind of the slang name for that. Another type of termination you have is a punch down termination. This comes from the days of phone. If I go way back in time to early phone, beginnings of phone, they would get punched into a 66 block. Here's a wall full of 66 blocks. Here's one kind of laying on its side. Here's a close-up of how you would terminate. You would punch wires into this side, use a little clip, and then punch wires into the other side. And that allowed you to connect PBX out to a floor, out to a phone kind of thing. You were doing lots of these punch-in terminations. The other type of termination they mentioned is a 110 block. This kind of was an evolution. This was an AT&T development, if you will. This was an evolution, being able to carry phone as well as data. This was some of the beginning data terminations here, using the 110 block. Well, if I look at my modern day patch panel, and the patch panels we'll use, here's the front where I plug a patch cable into. Here's the back where I punch my wires into, my horizontal cabling into. If I look at that back a little closer, where I punch my horizontal cabling into, dun, 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 it's a 110 block. Yep, that's a 110 block. So the patch panels that we're going to terminate into are 110 blocks. That's what we terminate our horizontal cabling into. They mentioned some fiber terminations. The common fiber terminations we run into, well, some of the very first fiber terminations was an ST connector, this kind here. That was, I would say, mostly replaced by SC connector. That was like the next evolution. This just kind of plugged in. Then some places adopted the MTRJ, which allowed both fibers into one connector. Okay, this was an individual connector. Both fibers went into one connector here, but they had some issues with fiber alignment, so most terminations now use the LC connector. When we terminate, actually when we plug fiber connections in between the routers and switches, we're going to be using LC cables. When we terminate fiber later this semester, we'll be terminating using an LC connector. That's pretty much the common connector used now. Here's a close-up of all those. There's the ST, the two fibers, C, the two fibers, MTRJ, both fibers are in there. There's one where that dot is, one where that dot is. And then here's the modern LC, connector. They mentioned power over Ethernet. Our switches are capable, or if we buy a switch capable, that's something we need to keep in mind. We would need to buy a switch capable of power over Ethernet. It can power things like phones, security cameras, access points, that sort of thing, through our unshielded twisted pair cabling. And there is standards for how much power can be sent to a device. And actually, each of these devices, if I look them up, would consume so many watts. So I might need to do a little math on what am I plugging in, so I know how much wattage my switch needs to be able to supply. If I try to plug in too many devices, usually the switches just don't power those last devices. Like, nope, I'm out. Too bad. So I might need to do some homework on what's needed. When we get to copper cable testing, which we will do as we're doing our cabling, as we're doing our terminations and our patch cables, we'll start doing some of this. We are going to use a series of meters to do so. Eventually, we're going to use a certification meter to certify our cable run, and that's kind of what they're talking about here. I'll hook up a tester across that run, and it'll run a battery of tests. One of the first ones it does is a wire map, all the wires in the correct order. If they're not, we cause signal data issues of data not going the correct place or the correct pin. It's going to test for length. Is it below the 100 meters? It's going to test for attenuation. Is the signal loss too great? It's going to test for crosstalk. Is there too much signal jumping from one wire pair to another wire pair? It's going to look at the attenuation to crosstalk ratio. If there's too much signal loss and too much crosstalk, the data is not going to get through. It's going to look at return loss, how much of the signal is getting reflected back. Well, it's looking at all these, and a lot of these we have control over when we terminate. Various things that we do. If we do too much of a untwist when we terminate our cabling, we can cause near-on crosstalk failures, stuff like that. So keep this part of the book in mind that we can look back to later when we start doing all these tests, because these will give you almost a little glossary of what all these values are, because we'll be testing later and we'll be talking about some of these later as well. They mentioned a multimeter for testing voltage and signal across cabling. We don't use too much of that in our lab room because we typically use meters like this. This wire mapper actually runs a test across the cable showing you the wire pairs and distance and so forth. So it gives us a little bit of more information than yes, there's a path there. Here's the certifiers we will use later this semester as well. This will run those, the battery of tests that we were looking up here, it'll run those battery of tests for us. Okay, so as we start doing that, we'll dissect some of those test results that we're getting back. For fiber optic, there's a lot less we have to test. We're basically testing is, can we get a signal across or is it broken? And then how much signal loss do we have? There is microscopes we'll use later this semester to look at the end of the connector to see if there's damage on the end of the connector. We will also hook up a visual fault locator. Ours looks like this. That's why I showed you this picture here. And if there is a break in the cable, you'll see it light up here. It actually just lights that up because the light hits that break and it kind of reflects out and lets you know that there is a break or a fracture at that point in the cable. One of the last tests we'll do is a loss test. We'll look at how much signal loss is across the fiber. And as long as there's not much, the fiber link is good. If there's too much, then we know there's going to be issues with that fiber link. That's pretty much the testing we do on fiber, this kind of stuff. And I have meters to test all these that we can try them out and see what the end of the cable looks like, where the fault might be, and if there's signal loss on the cable. So there's the last of the terminology from Chapter 2.